Advantages of high Mach flight. A presentation of Falcon Jet Corporation. Manufacturers of the Falcon 200, Falcon 50, and the incomparable Falcon 900. In the past 15 years, 15 business jets have been lost due to loss of control at high altitude or at high indicated airspeeds. These accidents have three primary causes: pilot factors, inappropriate wing design, inadequate control systems for the high Mach high altitude environment. This presentation is designed to review some of the concerns in high-speed flight and to show how Falcon jet design puts safety first. Falcon's safety is a matter of record. There has never been a high-altitude, high-speed loss of control mishap in a Falcon jet aircraft, nor has the structure of a Falcon airplane ever failed from the overstressing of severe turbulence or high speed. First, let's discuss what Mach number is and what it means to pilots of subsonic corporate jet aircraft. The term Mach number originated with Dr. Ernst Mach, an Austrian scientist. Mach 1 denotes 100% of the speed of sound. An airplane's Mach number limitation is expressed as MMO, Mach maximum operating. This usually becomes limiting between 18 and 20,000 feet. The indicated airspeed limitation is expressed as VMO, velocity maximum operating. VMO is primarily a structural limitation. MMO is primarily an aerodynamic limitation. To better understand Mach number, just imagine a sudden pressure disturbance in the atmosphere, a thunderclap, a gunshot, or a fast-moving aircraft. This pressure disturbance is transmitted by the collision of air molecules one against the other. The speed at which these molecular collisions propagate is the speed of sound. Mach 1, or 100% of the speed of sound at sea level on a standard day, is 760 miles per hour, or about 660 knots true airspeed. Since the speed of sound decreases with temperature, it is lower at cruising altitudes than at sea level. Corporate jets typically fly at 50 to 80% of the speed of sound. An airplane's ability to cruise safely and efficiently at a given Mach number is largely a function of its wing design. Wing shape and the degree of wing sweep determine the most economical cruise Mach number. Given more sweep, a wing can provide even higher economical cruise speeds, although there is some penalty in range and runway requirements. Dassault has overcome the problem of increasing cruise speeds and Mach numbers without increasing wing sweep. Instead, the computer-designed wing of the Falcon 100, for example, is optimized for high speed by reshaping to modify the wing's pressure pattern. This is similar to NASA's supercritical wing. Computer-designed high-speed wings are relatively thick, which allows the installation of high-lift devices. They also have greater strength with lighter structure, while allowing economical cruise speeds equal to or greater than earlier thin-wing competitive designs. And they provide more room for fuel, so that external tanks are not needed. At low Mach numbers, aerodynamic friction drag constitutes the major portion of airfoil drag. But as Mach number increases, a point is reached where the drag from the shock wave predominates. The reason for this is that as airspeed increases, the airflow accelerates until at some point the local Mach number on the wing's upper surface becomes sonic, or Mach 1. This is the wing's critical Mach number. If the critical Mach number is exceeded, an area of supersonic airflow is created and a normal shock wave starts to form. With an increase in speed of only 5 to 10% beyond the critical Mach number, the shock wave is weak. However, a Mach number is reached eventually which produces a strong shock wave and a sharp increase in drag. This is called the drag divergence Mach number. At this point, the shock wave is strong enough to alter the pressure distribution over the wing. This causes a decrease in lift and a change in the pitching moment as the wing's center of lift moves aft. The nose pitches down, causing speed to increase. This is the beginning of Mach tuck. Mach tuck involves two basic aerodynamic forces. First is the decreased effectiveness of the elevator caused by airflow separation due to shock wave formation. The second destabilizing force is the aft movement of the wing's center of lift as Mach number increases. This causes the aircraft to pitch down, increasing Mach number and aggravating the problem. Left unchecked, the consequences are disastrous. When an aircraft exceeds its limiting Mach number, the turbulent wake behind the shock wave may cause a high-frequency buffeting in the flight control surfaces. With any type of reversible control system, the ailerons may bounce from stop to stop, a condition called aileron snatch. Prolonged or severe buffeting can result in structural damage or failure. In addition, separation of the boundary layer air by the shock wave results in decreased flight control effectiveness. In some instances, aileron control forces seem to reverse, and the elevator control force becomes extremely heavy. So an accidental excursion over the limiting Mach number can result in control surface buzz, loss of normal control surface authority, and aggravated Mach tuck. In the Falcon jet family, these control problems are not noticed. Thanks to an irreversible hydraulically actuated flight control system, the control surfaces are held rigid to prevent buzz or aerodynamic feedback to the pilot. The hazards of airflow separation are minimal in the Falcon jet family of business jets, with their swept wings, high-speed airfoil design, and hydraulically powered flight controls. Another phenomenon found in several types of corporate jets is Mach pitch. If the wing tips shock first, an aeroelastic twist rotates the tips and causes the center of pressure to move forward. In some aircraft, the wings shock unevenly, and a rolling moment is generated toward the wing that shocks first. A combination of these forces can result in Dutch roll, a rolling and pitching motion. This can be corrected only by decelerating. Some aircraft require yaw dampers at higher altitudes. Dutch roll makes hand flying at high altitude extremely difficult in some aircraft. By applying fighter technology, Falcon jets have none of these characteristics. They remain stable in pitch, yaw, and roll throughout their flight envelope. In fact, Falcons behave well not only to MMO, but .05 beyond. This is their MDF, or Mach demonstrated flight number. An accidental Mach excursion can be caused by a change in aircraft attitude or a rapid change in atmospheric conditions. Increases of as much as .05 Mach have been known to occur in a matter of seconds. In many jets, this is a real emergency. Above MMO, extension of spoilers often makes things worse. Reduction of speed may require landing gear extension and possible loss of the gear doors. Falcon pilots have more time to react to Mach excursions due to the extremely high MMO, higher than competitive aircraft. In addition, Falcon air brakes may be extended above MMO without destabilizing the aircraft. What of the hazard called coffin corner? It's just not a problem in Falcon jets, but it can have serious consequences in several other types. Here's what happens. Every airfoil has an aerodynamic ceiling, where the high-speed and low-speed buffet boundaries merge. In that rarefied upper atmosphere, stall speed increases. This so-called low-speed buffet boundary is actually pre-stall buffet. It's caused by the combined effects of reduced air density and Reynolds number and the need to fly a higher angle of attack to maintain a target Mach number and altitude. In an effort to maintain a target Mach number of, let's say, 0.80, angle of attack must be increased, moving the stagnation point down the leading edge of the wing. Airflow over the top of the wing must accelerate as it has further to travel. The result is a higher local Mach number over the upper surface of the wing, generating a shock wave at a slower speed than at lower altitudes. The onset of low-speed buffet is a direct function of aircraft gross weight, altitude, and temperature, coupled with bank angle and G-loading. The safety margin between low and high-speed buffet boundaries is best measured by indicated airspeed. For example, the 1G buffet-free range for a particular non-Falcon jet airplane at flight level 350 is from 187 knots indicated on the low-speed side to 279 knots on the high-speed side. At flight level 450, however, the buffet-free speed range is reduced by 77% to 192 knots indicated on the low-speed side and 212 knots on the high-speed side, a spread of only 20 knots. This is not a problem in any of the Falcon jet aircraft. For example, the Falcon 100 still maintains a 50-knot spread between low-speed buffet and its .87 limiting Mach number at its maximum certified altitude of flight level 450. The Falcon jet's exceptional high-altitude buffet-free envelope is superior to competitive models. We designed it that way. This means added safety during a clear air turbulence encounter or accidental thunderstorm penetration. Now let's discuss turbulence penetration speeds. Aircraft manufacturers establish a turbulence penetration speed for each of their transport aircraft based on structural considerations. In competitive aircraft, this speed is often the same as maneuvering speed. At maneuvering speed, a sudden full-scale deflection of the elevator, rudder, or aileron will not result in structural damage or failure. The aircraft will stall rather than be overstressed by G-forces. In fact, under current certification standards, full rudder deflection at VMO must also be demonstrated. Falcon jet aircraft are so inherently strong that they are certified for flight through turbulence without speed restrictions. They can fly up to VMO or MMO as applicable. No other business jets have this capability. The Falcon 100 has an established maneuvering speed of 220 knots indicated airspeed. At flight level 450, this is Mach .80. Competing designs are limited to Mach .73. At altitude, severe turbulence can quickly produce a gust-induced stall. In some T-tailed aircraft, this can lead to a locked-in deep stall. T-tailed aircraft with a locked-in deep stall problem are thus required to have an operational stick shaker and/or stick pusher system, which reduces this hazard. But a gust-induced stall is still possible. With the autopilot on altitude hold, a sudden strong downdraft, mountain wave, or high-altitude wind shear can quickly place the aircraft below stick shaker airspeed, and control may be lost. Following a gust-induced stall, with the nose now lowered for recovery, suppose a strong updraft is encountered. The result will be a rapidly building airspeed and Mach number. The instinctive pilot reaction is to trim and pull the nose up. But at high altitude, as little as half a G puts some aircraft into buffet, and the nose will not come up. Or, if the autopilot is flying the airplane, it will push the nose down in an effort to hold altitude. In either case, airspeed builds rapidly, and the limiting Mach number is quickly exceeded. Without a Falcon-type irreversible servo control system, an accidental overspeed may expose the aircraft to the hazards of control surface buzz, aileron snatch, Mach tuck, and the loss of elevator control authority. Meanwhile, slowing down may put the aircraft into low-speed buffet. Such is the dilemma of Coffin Corner. In the Falcon series, the irreversible hydraulic controls and aerodynamically advanced swept wings work together to eliminate these hazards. Some corporate accidents have occurred during dives at low altitude, where shock-induced flow separation is not a factor. In some instances, G limitations have been exceeded, and the tail or wing structure fails. In jets not equipped with servo controls, as indicated airspeed increases, the elevator control force required for dive recovery increases, and after the limiting airspeed is exceeded, the elevator may seem immovable. The hydraulically actuated flight controls used in the Falcon jet family of airplanes prevents this hazardous situation. Because in a Falcon jet, as airspeed increases, the pilot continues to enjoy a comfortable elevator control force, while the mechanical advantage on the elevator becomes more restrictive to prevent sudden overstress by an overzealous control application. Following a severe overspeed, evidence of aerodynamic flutter has been found in some jet upset accidents, but never in a Falcon. While any airfoil will flutter given enough airspeed, Falcons have been flown by test pilots in maximum speed dives to 445 knots indicated, or 75 knots faster than VMO, and studies show that flutter speed is far in excess of the dive speed. Falcons are designed so that an accidental overspeed at high altitude will tend to be self-limiting due to shock-induced drag. Flutter speeds will not be reached. During a normal descent from cruise altitude, it is the same shock-wave-induced drag that caused Dassault to publish a fuel-efficient descent schedule of 0.8 Mach number intercepting 320 knots airspeed, avoiding excessive drag rise. To make the Falcons even more comfortable and safe, Falcon engineered high-lift leading-edge devices and slotted Fowler flaps. These lower approach and landing speeds while retaining the docile flying qualities of a Falcon jet in cruise. To increase the lift produced at low speeds, Dassault uses hydraulically operated full-span leading-edge slats. These slats change the wing's camber, producing greater lift at high angles of attack. The outboard slats improve airflow over the ailerons, improving low-speed handling. The inboard slats generate most of the lift by improving the airflow over the trailing edge flaps. The slats are extended and held rigidly in position by hydraulic actuators. Hydraulically operated slats have the advantage of remaining fixed in position during a landing approach in turbulent air. Aerodynamically operated slats on some aircraft can slide in and out in turbulence, constantly changing the coefficient of lift. When the slotted Fowler flaps extend, they increase the wing's chord as well as its camber, thus increasing the lift significantly in the first half of extension. When fully extended, they lower the stall speed substantially and provide drag for a slow landing approach and touchdown. In fact, these high-lift devices are so effective that swept-wing Falcons routinely perform as well or better than straight-wing designs. For example, despite the fact that the Falcon 900 is approximately 3 times as heavy and nearly 100 knots faster than a Citation II, VREF with 8 passengers and NBAA IFR reserves is only 4 knots higher, and the runway it requires for a 1,500 nautical mile trip is actually less. We've told you how well Falcons handle at high Mach numbers. Now we're going to show you by taking you into the cockpit of a Falcon 50 with Ed Allen of Falcon Jet Corporation and Hervé Le Prince Ringuet of Dassault. The demonstration you're about to see is unforgettable. While this is not the recommended way to operate the aircraft, it provides dramatic evidence of the Falcon's superior capabilities in high Mach flight.
Today we would like to perform a high Mach demonstration for you. We're in our Falcon 50, but we could be in any Falcon, but not in just any business jet. This is due to the hydraulically powered flight controls, to the excellent aerodynamics of all the Dassault aircraft and all the Falcon aircraft. Hervé, could you block the airspace, please?
West control, Falcon Fox Bravo India November Romeo. Can you block an altitude for us between 430 and 310 heading to sharp? Fox Bravo India November Romeo, descend for level 310, direct to sharp. Thank you. Direct to sharp, shoot down to 310.
The purpose of the high Mach demonstration is to show you that the Falcon 50 and all our other Falcons can fly at its limiting Mach and beyond without any problem. As you can see, we're now at Mach 8.2. We're at flight level 430, and our weight is 26,000 pounds. So we'll go ahead and get started by first disconnecting the autopilot and the flight director and start a slight descent. The noise that you hear now is our trim clacker moving, which is a normal sound that you would hear in the cockpit. Okay, our Mach has started to increase a little bit to Mach 8.3, Mach 8.4, 8.5. There's our Mach warning limit at 8.65. We'll continue to accelerate. We're at Mach 9.0. And we still have no buzz, no vibration, and certainly no problem to fly the aircraft at this Mach. We can bank the aircraft left and right, 45 degrees of bank or more. You see there's still no tuck, there's no vibration to worry about whatsoever. We'll continue to accelerate, and now we're flying at 9.4, 9.5, 9.6, 9.7. We'll go ahead and trim hands off and see no problem, steady as a rock. Even our true airspeed now is 520 knots. We can do a 2G pull-up. Even at 9.1 when we finish with the pull-up. We can use our speed brakes to decelerate with no problem whatsoever. Here, if you take it, we'll decelerate now and get back to our normal cruise envelope. This just goes to confirm that the Falcons and all Dassault aircraft have a lot of inherent strength designed into them, and that they have excellent handling characteristics. Thanks very much.
Falcon conquers high-altitude, high-Mach flight through superior design. Irreversible, hydraulically actuated flight controls prevent undesirable aerodynamic feedback with solid controllability at all airspeeds and Mach numbers. Falcon pilots do not have to contend with Mach tuck, aileron buzz, or other dangerous characteristics. In the event of an inadvertent Mach overspeed, air brakes may be extended without creating the instability commonly associated with spoiler extension in competitive aircraft. And the Falcon's wing design means no worries about Coffin corner or turbulence upset at certified operating altitudes. A Falcon jet does not require a stick shaker to warn of impending stall. No stick puller is required to prevent Mach tuck following an inadvertent overspeed. And there is no requirement for extraordinary pilot strength to recover from a high-speed dive. To operate a Falcon jet at high altitude and in turbulent air, you don't require an autopilot or yaw dampers. In fact, all you need to fly a Falcon jet is the airframe and engines. Falcons are engineered for safety throughout their operating envelope and beyond it as well. Their rugged structures, powerful control response, and superior aerodynamic design make them the only family of business jets that are totally at home in high Mach, high altitude flight.